All right, class. For the next lesson of our Module 8 series, we are going to go to what 8.1c lesson, which is on simulations and random sampling. Okay, so we're going to move a little bit away from the math calculation side of statistics, and we're now going to talk about the importance of random sampling. Okay, so it says, can you roll your tongue? What fraction of the class can roll their tongues? Um, if this is considered rolling your tongue, I can definitely do it. I know not everyone can do it, but that would be a fun question that we could ask the class if we were in school. But according to a nationwide survey, let's say, approximately 1 out of every 3 people cannot roll their tongue. Does the class survey match the expected 1 to 3 statistic? So you could see that even though the statistic is 1 out of 3 cannot roll their tongue, is it possible, class, that the entire class, period 5 or period 6, none of them can roll their tongue? Right? So remember that this is the theoretical probability, but it's very, very possible that our experiment, when we survey people, it actually doesn't work, right? So number 2 says Ria is doing a survey on the number of people with different genetic traits. She asks people one at a time if they can roll their tongue. Ria was surprised that she asked 5 people before she found someone who wasn't able to roll their tongue. Does this mean that the statement approximately 1 out of 3 people cannot roll their tongue is false? Well, what do we think, class? Right? No. All this means is that Ria's experiment did not exactly match, right? Did not exactly match with the previous estimation. But that's okay, class, because it doesn't mean that it will happen. It will always happen. Is it unusual that after surveying 5 people, she did not find anyone who could not roll their tongue? No, I don't think it's unusual. I just think that's what probability says, right? Now, it is not unusual. However, if she surveyed 5,000 people, if she surveyed 5,000 people and did not find someone and could not find someone, that would be weird. That couldn't roll their tongue. That would be suspicious, I would say, right? Now, remember, class, statistics are always based off of previous events, previous um, experiments, right? So if we say that 1 out of 3 or 1 out of 3 people cannot roll their tongue, and you survey 5,000 people, and why did I choose 5,000? Because 5,000 is a very large number, right? And all I'm just trying to prove the point is if you survey a lot of people and you're realizing that it's not anywhere close to 1 out of 3, then you might want to reevaluate the 1 out of 3 ratio. Okay, so what Ria just did was a simulation. A simulation is an experiment that tests, that models a real life situation, right? Models a real life situation. Okay. Um, and the simulation is just basically like kind of like saying if I have a die, and I say your outcome of getting a number 1 is 1 out of 6, and you can simulate that by rolling the die, and you can see if that's true. Now, remember, just because the probability is 1 out of 6 doesn't mean that you are guaranteed to get a 1 out of every 6, right? Is it possible, class, that when I'm rolling my die, Is it possible that I never get the 1? Even if I roll it maybe 60 times? It's not, it's very, very, very unlikely, but it's not impossible, right? So a simulation is just to test to see if an outcome is truly as difficult as it sounds. But you have to realize that not all simulations will match exactly what you think the outcome should be, right? Just because if I roll a die 60 times, does that mean I will get 10 ones and 10 twos and 10 threes, and it will be an exact match with the probability? No. This goes back to the idea of what is considered theoretical, what is considered experimental. Okay. Theoretically, you should get 10 ones, 10 twos, 10 threes, 10 fours, 10 fives, and 10 sixes. But we all know that that's not always possible. And that's probably not going to happen, actually. Okay, so you can see how this example is going to talk about more about rolling the die. I'm not going to go over that, but I do want to talk about something that I kind of already described, and it is the law of large numbers. The law of large numbers basically says that your experimental probability, right? The experimental probability obtained from a large sample size, from a large, very large sample number of simulations is more accurate, right? Number of simulations is much more accurate, is more accurate, and approaches the theoretical probability. So, basically saying that if you want your experiment to be more accurate, you have to have a large sample size. The larger sample size, the more accurate. Okay, the better foundation, the better we can use this estimation as a good sample, right? And you realize, obviously, whenever you're doing a simulation, you always want to simulate with a large sample size, because if you just, like, a quick example of that, class, is if I were to flip a coin 4 times and I got 3 heads and 1 tails, that's my simulation. But what if I were to get 4,000 flips instead of just 4? Do you really think that I would get 3,000 heads and 1,000 tails? No. Now, is it possible that I get 3,000 heads and 1,000 tails? Yes, but most likely, since I have more flips, the probability will start to kind of reset itself, and it will start to even out and balance out, because essentially the probabilities are always the same. So there's no reason why I should be getting more heads than tails. Now, again, the beauty of probability is we never know. But I would estimate that if I were to get 3 heads and 1 tails and 4 flips, but then I changed it to 4,000, you might get something like this. Right? 2,200 heads and 1,800 tails. Now, heads is still the clear winner, but you can see how the probabilities are closer and closer, right? And then if I do 400,000 flips, which is a very enormous amount, I might actually end up with 205,000 heads and then 195,000 tails. And you'll start to see that these odds are much better. These odds are much more balanced than the original 3-1. Okay, so that's just a very, very quick example of, if you want a more accurate outcome and you want to see the event with the number or with the best accuracy, you would have to increase the event amount by a lot. You want a large number. All right. Okay, so we're going to shift gears a little bit, and we're now going to talk about surveys. We're going to talk, and the reason why we talk about surveys with probability is because whenever we survey people, we want to make sure that we use the right criteria to survey. Okay, so An example of this is if you want to know someone's favorite fast food restaurant, would you ever stand outside of an In-N-Out and ask them what their favorite fast food restaurant chain is, right? You'll start to realize that that's not the best way to conduct information. That's not the best way to conduct a sample, because that would be a biased sample. Okay, so a random sample is an unbiased, bias meaning having a favor for something, right? An unbiased representation of a group. You want to make sure that whenever you're sampling someone or something or some topic, you want to make sure that the selection is chosen randomly, right? Sometimes statistics can be very, very misleading because unfortunately the sample is not random, right? You want your sample to be random because you want your sample to represent the population. If your sample is not random, then it's not really indicating something of the population. If you ask Mr. Kuo what his favorite dessert is, and just because you ask Mr. Kuo that, can you make an estimation of all the teachers at Pacific Trails? No, right? And specifically, if you already know what I like, then you already know the answer, and it's just like it's not really a survey anymore. You're kind of like biasing your interview questions to me because you already know what I like, and you're kind of slanting the outcome already. So that's one of the worst things you can do. But unfortunately, the reality is a lot of people, accidentally or purposely do that. So that's kind of like the downfall of surveys. Okay, so we're now going to read a few examples of what is considered a good random sample and maybe what is not the best random sample. Okay, so let's read this. The PTSA wants to increase the number of students who eat hot lunch at school. The leadership class has been asked to conduct a survey of the student body to determine the students' preferences for hot lunch. They have determined 2 ways to do the survey. The 2 methods are listed below. Survey the first 20 students that enter the lunch area, or survey every 3rd student who gets off the bus. Which of these 2 do you think is a better indication of the school population? If you want to know who likes to eat hot lunch, would you be surveying the people at the lunch area, or would you be surveying the people that are leaving the bus? Right? Which survey option is better? Now, if you said the bus, you are correct. The bus survey is a better way to collect data because it doesn't revolve around people that already are eating the lunch. If you go to the lunch area, you are considered a lunch customer already, right? So it's not really a good indication of how we could improve the hot meals from the lunch cafeteria, right? The bus survey is a better way to collect data because it does not involve cafeteria customers already. Known involve cafeteria customers. Okay. Surveying the students in the lunchroom would be biased. And bias is the worst thing you can do for a survey. All right. We're now going to, after this, we're going to go over more examples of what's considered biased, what's considered random. And random is always the best way to collect data. And I'll see you in the next video. Thanks for watching.